Hi guys, it's Daniel here, and today we're going to do AIME 2 from 2013, and this is problem number 14, so it's not a very easy one. So first let's look at the problem. For positive integers n and k, let f of n comma k be the remainder when n is divided by k. And for n greater than 1, let fn equals the maximum when k ranges from 1 to n over 2 of f of n comma k. Find the remainder when sum from n equals 20 to 100 of f of n is divided by 100. So first of all, when we first read this question, it's really overwhelming with all this confusing notation with like f of n comma k and then the sum from n equals 20 to 100. So it's all really confusing and overwhelming. So for these types of problems, the first thing I like to do is to sort of get a sense of how the problem works. And to do that, for this problem, I just first list out values of big F. So, for example, f of 2. So what does f of 2 even mean? So let's look at this definition here. F of 2 equals the maximum when 1 is less than or equal to k is less than or equal to n over 2, which is 2 over 2, which is 1, of f of 2 comma k. So this doesn't really reveal anything important to us or insightful to us because k can only be one value, so there really isn't any point. And we continue on to see if there's something else that might give us something nice, and we find that f of 3 is still 0. F of 4, still 0. But f of 5 is the first interesting case. Let's look at it. So f of 5 is the maximum as k ranges from 1 to, well, 5 over 2, that's 2.5. So in essence, k is equal to 1 or 2 of f of 5 comma k. So let's see what happens here. What we do here is we compare all the possible values of k. So f of 5 comma 1 and f of 5 comma 2, and out of these two values we find the maximum. So clearly f of 5 comma 1 is 0 because anything divided by 1 has a remainder 0. However, f of 5 comma 2 is equal to 1 because when we divide 5 by 2 we get a remainder of 1. So out of these two, clearly f of 5 comma 2 is the greater one, so big F of 5 is equal to 1. And then this is all nice and well, but we still don't really have any idea how to find the value of big F of n for general n. So what I do is I just keep on listing values. F of 6, you find it's 0. F of 7, you find it's 1. 8, you find it's 2. 9, you find it's 1. 10, you find it's 2. 11, you find it's 3. 12, you find it's 2. 13, you find it's 3. 14, you find it's 4. 15, you find it's 3. And maybe perhaps by now you've noticed a pattern. Let's group it by 3's. If you group this part, we see that it's 0, 0, 0. If we group the next part, it's 1, 0, 1, and then 2, 1, 2, 3, 2, 3, 4, 3, and what would you think big F of 16 would be? We'd think it's 4, right? And it turns out, indeed, when we list out the possible values of little f, indeed, the value of big F of 16 is 4. So this pretty much confirms our pattern, and by now, since this is an AIME and it's only asking for answers, you can basically just find the sum from n equals 20 to 100 of big F of n just by using this pattern and solving. But since this is not the AIME that we're doing right now, it's just a video, that's no fun. So we're going to actually prove that this is indeed the correct values of big F of n. So to first do that, we need to first turn this into algebra. First, quantify it. So what does this pattern actually mean? Well, note that since we're grouping by 3's, let's do casework on whether we're doing f of 3n for some positive integer n, or non-negative more like, f of 3n plus 1, or f of 3n plus 2. And note that these cover all possible natural numbers because it represents the 3 different residues modulo 3, which is 0, 1, and 2. So our pattern tells us that f of 3n is equal to n minus 2, f of 3n plus 1 is equal to n minus 1, and f of 3n plus 2 is equal to n. You can confirm that this is indeed the correct values. Now first I'm going to prove that f of 3n is equal to n minus 2. So let's move over here. F of 3n equals n minus 2. That's our proposition. So now let's see how to prove this. So suppose that this is in fact not true, and that f of 3n equals some bigger number, like x, which is greater than n minus 2. And, well, first of all, we have to show that f of 3n equals n minus 2 is in fact, like, possible. So you can actually find a value such that it gives n minus 2. And this is actually not that hard. Just choose k equals n plus 1. Okay, when k equals n plus 1, 3n divided by n plus 1. Okay, well, it fits in 2 times, and what's left over is 3n minus 2 times n plus 1, which is equal to n minus 2. So we see that this is actually a possible remainder, and it is attained when we divide by n plus 1. So now, let's suppose that there exists another remainder, call it x, such that it's greater than n plus 2. N minus 2. So what does that mean? That means that there exists a k. There exists a k such that it divides 3n minus that remainder x. Correct? And in fact, this 3n minus x, by using our inequality here, is less than, well, 3n minus n minus 2, which is equal to 2n plus 2. So our right-hand side of this divisibility here is less than 2n plus 2. And since we know that k cannot be, well, actually, let's suppose that it's possible that k equals 3n minus x. Well, is this possible? It would mean that x plus k equals 3n, right? But that would, since x is less than k, since it's the remainder when we divide by k from 3n, it follows that this entire expression is less than 2k. But it's equal to 3n. So it follows that 3n is less than 2k, which means that k is greater than 3n over 2, which is not possible, as in our definition here, we know that k is less than or equal to what we plug in for n here, which is 3n. So k is less than or equal to 3n over 2, which is obviously not possible. So therefore, this is wrong. And that means that it follows that since k cannot be equal to 3n minus x, it has to at least be twice as small as 3n minus x. Because we can't multiply k by something between 1 and 2 and get a divisibility, because that just doesn't make sense. So it follows that k divides, or k is less than n plus 1. So now we know that k is less than n plus 1. So does this give us anything bad? Well, first let's just make it less than or equal to. And also, we look at this x. X is greater than n minus 2 means x is greater than or equal to n minus 1. Well, that's kind of restrictive. We know that k is less than or equal to n, and x is greater than or equal to n minus 1. And since x is a remainder when we divide by k, x must be less than k. So therefore, in fact, x is equal to n, and or k is equal to n, and x is equal to n minus 1 because k is greater than x. So now we have reached a desired contradiction, because if k is equal to n, then when we divide 3n by k, then we get a remainder of 0, which is clearly not equal to n minus 1. So therefore, we have reached a contradiction here, and our assumption that there exists an x that is greater than n minus 2, such that there exists a k between 1 and 3n over 2 that satisfies this, that's like all wrong. So therefore, our value of k equals n plus 1 gives the maximum value of big F of 3n. And in fact, you can actually do this proof for f of 3n plus 1 and f of 3n plus 2 equals n minus 1 and n, respectively. It's basically exactly the same thing. So now we've just established that the value of big F at these three values is these three numbers, respectively. So we've just proved our pattern that we found over here, and now we can use this pattern to find the sum from n equals 20 to 100 of f of n without any qualms. And once you do that, I'll just skip the calculation because it's really boring. You get that the remainder when the sum is divided by 100 is equal to 512, and this is our answer.
We're going to be doing some AMC 10 practice videos, and here's AMC 2004 10B 25